Morning. So biomagnification, our focus today is to really go through the biogeochemical cycles. The biogeochemical cycles, it is exactly what it says it is. Right? Bio means living tissue. Geo means involving the earth, geology, rocks. Chemical is the cycling of matter or chemicals. Right? So we have our biogeochemical cycles. Geo is just comprised of the earth, so locked in sediments, rocks, things like that. So it really kind of hints to the cycle. Bio is the cycle in this material, right? These chemicals cycle through living things, bio. They also become a part of the Earth's components, such as rock or sediments, and they cycle between the two. The chemicals we're talking about are carbon, nitrogen, phosphorus, water are the key cycles we focus on. Why do we focus on carbon? Why is carbon cycle such a big deal? Okay, what's that mean? We are made from carbon molecules, right? So organic chemistry is the study of carbon chemistry. Lipids, carbohydrates, proteins, nucleic acids, the backbone of all those molecules are carbon. Where do we get our carbon from? The carbon cycle, we know the carbon cycle involves CO2, right? It's been increasing because of global warming, climate change, all that good stuff. How do we get carbon in the carbon cycle, though? It's where people always mess it up. How do we get carbon in the carbon cycle? Plants get it through photosynthesis, right? Taking in carbon dioxide out of the atmosphere. How do we get carbon in the carbon cycle? We eat, right? We eat. We get carbon from our food chain. So of course you have the photosynthesis respiration aspect, right? Where photosynthesis takes in carbon dioxide, respiration releases carbon dioxide, right? But where do we get the carbon to release the carbon dioxide? We get it from the breakdown of food, glucose, right? Big respiration. So just think the food chain's a part of it. What do we? So we kind of talk about carbon. Nitrogen. Why is nitrogen a key cycle that we focus on? What is a key macromolecule we need nitrogen to make? Amino acids, right? Proteins, the amine group, the nitrogen. All of our proteins need nitrogen, so therefore we need nitrogen to make proteins, to make amino acids. Also nucleic acids. DNA has nitrogen as well. Phosphorus is a cycle. Which molecule requires lots of phosphorus? 5 carbon sugar, nitrogenous base, and a nucleic acids, DNA, RNA, right? There's a 5 carbon sugar, nitrogenous base in the phosphate group. Also, what is our molecule of energy? ATP, which is a nucleic acid as well, right? Phosphorus. That's when we talk about the phosphorus cycle. It's linked to what we need to make organisms. So the carbon, the nitrogen, the phosphorus, just realize the food chain is a key component to all of these. We kind of focus on the atmospheric aspect, but the food chain is part of it. And why do we need them? We need them to make all of our organic molecules with carbon. We need it to make proteins, nucleic acids with nitrogen. We need it to make nucleic acids, energy molecules with phosphorus. Okay. The first cycle is the hydrologic cycle. It involves 2 key processes to start it off, right? Water needs to go from a liquid form to a gaseous state. We call that evaporation. Does water evaporate easily, or does it take a lot of energy to form? It's National Teachers Day. You're going to have your phone out in your lap. Are you kidding me? All right. How come does water evaporate easily, or does water take a lot of energy to evaporate? It takes lots of energy. It has a high, what do we call the energy needed for water to evaporate? What? Not specific heat, but you're in the right ballpark. Specific heat is how much energy it takes to change the temperature of water. There's a different term for how much energy it takes for water to vaporize. Heat, it takes a lot of heat to help water vaporize. The heat of vaporization. You never heard that before in your science classes? No. All right. So with carbon, right, we have the heat. With water, evaporation involves the heat of vaporization. The heat of vaporization is the energy needed for water to go from a liquid state to a gaseous state. What bonds does it need to break free of in order to vaporize? Hydrogen bonds, right? Hydrogen bonds play a role here. Water is polar. Big concepts. All right. Transpiration is evaporation. It's simply just evaporation from leaves from plants. That's it. Same thing, just evaporation from plants. So the hydraulic cycle, we kind of usually start there, right? Here's kind of the evaporation from the water in the environment, the transpiration from the leaves of these plants, and so forth. Okay. I feel like this is like, now we revert back to second grade science, right? All right, children. Here is the water cycle. The water cycle starts with evaporation and transpiration. That is water going from a gaseous state to from a liquid state to a gaseous state. Water vaporizing. What does water do? Right? That warm, moist air is doing what as it rises? Okay. It is cooling, and it is cooling and condensing, right? That is making clouds. That's exactly what's going on, right? As it rises, it's cooling. When things cool, molecules get closer together. So therefore, you're not kind of having this, I guess would be kind of transparent water vapor. It's not condensing, and it's starting to become opaque. You start to actually see it like clouds. Right? If it continues to condense, and you get more and more water vapor back together, eventually you might get, right? It's what do we call rain? You're a little rain is what? Like something like crying. Angels crying or something like that. Whatever it was. That's not what it is actually. It's actually just clouds releasing their moisture. So precipitation happens, right? The clouds have condensed so much, there's so much water vapor packed together that it can't hold it anymore. So it goes from a vapor back to a liquid state, and it drops as raindrops. So precipitation hits the ground. Right? At this point, we get surface water, and we also get groundwater. Some water will be collected in rivers, in lakes, in streams, in ponds. Some will make it all the way back to the ocean. Some water will actually be absorbed into the earth and kind of be part of our water table, groundwater. Like that's why we dig down for wells, because there's water deep down. So when you go to the ocean and you start digging a hole, it gets wet when you get down deep. Right? There's water in the water table. The water table is key, right? So we have what we call runoff, right? So we can have surface or groundwater. This is key because it actually is part of the filtration process. Like it's filtering the water, cleaning out the water as well. Eventually, all that runoff can start the cycle again and evaporate. Evaporate. Are we doing the water cycle? Pretty easy, right? Okay, good. So there's the water cycle. The nutrient cycles. Other key aspects that we need to look at. Again, this is the carbon, the nitrogen, and the phosphorus cycles. Every little organism needs nutrients, materials, building blocks to grow, carry out select processes. Right? Key ones being nitrogen, phosphorus, carbon. Nutrients are passed between organisms and their environments. We can kind of think of it as like reservoirs. So organisms are a reservoir for these cycles. It's an area where these materials, this matter, can be stored. The atmosphere is another reservoir. So it can be in the air. Not all of them are atmospheric processes, but it can be in the atmosphere, such as carbon dioxide or nitrogen gas. Another reservoir could be the earth itself, rocks, sediments. Right? Is another reservoir. So those are kind of like the three main reservoirs where this matter can be stored, and it's going to cycle between those reservoirs. How do you spell a reservoir? Reservoirs. So our reservoirs are atmosphere, so those are kind of like the key reservoirs for all of these cycles. Phosphorus is a little different. There's no atmospheric components of phosphorus. Okay. The carbon cycle is what we know the best. You need to memorize it. You need to know every aspect, every arrow on this document. You want me to simplify it for you? Right. The phosphorus cycle is actually very, very simple, very straightforward. So, okay. So I have CO2 coming out of the atmosphere, CO2 going into the atmosphere. That's really how the best way to break down the carbon cycle. What takes carbon dioxide out of the atmosphere? What processes on the board here take carbon dioxide out of the atmosphere? Photosynthesis.
CO2 in ocean.
Photosynthesis is the key one. Okay. I start photosynthesis, that is the key player here. I just put photosynthesis, dissolve CO2 in the ocean as a secondary one because there's limitations. The ocean just can't continue to absorb as much carbon dioxide infinitely. So depending on temperature in these areas, it could be absorbing or releasing carbon dioxide depending on environmental factors. So it typically, yes, it is absorbing CO2, but there's limits there. So that's not just, hey, we'll just let the ocean dissolve. Well, you dissolve CO2, what happens when carbon dioxide dissolves in water? The water becomes carbonated, right? That's what it is. It's carbonated. What's the pH code? So 3 on the pH scale. Same with seltzer, right? So when you dissolve carbon dioxide in water, the water becomes acidic. Think ocean animals or freshwater animals enjoy acidic water. Especially coral reefs. So the acidification of oceans is a big deal because of this. So that plays a big role. Is there anything else that takes carbon dioxide out of the atmosphere? No. See our problem here? What puts carbon dioxide into the atmosphere? Now let's deal with nothing man-made. Right?
Vibration.
Volcanic activity, all of these, right? They put carbon dioxide into the atmosphere. For a long time, we were good. For a long time, these sets of processes were, for the most part, balanced. Then something happened in the 1850s.
Factories.
What?
Oh, never mind.
What'd you say? Blackberries?
No factories.
Oh, I thought you said blackberries.
No factories.
Factories, like the Industrial Revolution. Right? Human population spiked. Why did human population spike? Because we found a source of cheap energy. Before that, how did you farm? How did you build? You used water power, hydropower. You used animal power, like oxes to pull your plow. Right? So therefore there was a limitation on energy, so their population is going to get so large. Industrial Revolution happened though, we found a cheap source of energy. Fossil fuels, carbon, coal, natural gas. We didn't use natural gas initially, but oil. Right? We use all of these. When that happens, this became unbalanced. We put far more carbon dioxide in the atmosphere than we take out of the atmosphere.
So now the summer is way too
And this process is not slowing down, right? This is linked to climate change, global warming, right? If you want to kind of talk about this, it's pretty easy to show. Take an aquarium, measure the temperature in that aquarium, increase carbon dioxide in that aquarium, measure the temperature. The temperature goes every time. There's no question about it. It goes up. We are increasing carbon dioxide levels. We just hit, I think it was like 409 parts per million was the last reading at the Mauna Lea Research Center in Hawaii. It's one of the places where they measure carbon dioxide levels. They measure with balloons going up into the atmosphere, taking air samples and bringing it back down to analyze. They do it there, research there, but it's also far removed from cities and factories, right? So you get kind of a real natural sample. They hit 409 parts per million. That's been 409 parts per million for about 15 million years. So it's pretty high. It's getting higher and higher. We have been 1 to 1.5, 1 3/4 degrees above the average temperatures for the past 11 months. So if you look at the temperatures between 1950 and 1980, you take the average number, right? You take our average temperature for the month of January, February, March, right? And you compare those two, the temperature from these past 11 months on average have been 1 to almost 1.5, 2 degrees warmer every month. Total temperatures every month in the past 11 months. Right? This is not going away. This is a bigger and bigger deal. Our storms are changing. I mean, look at this crazy winter. Winter was like literally 2 days. Like we had a storm. It was 72 degrees on Christmas Eve. One storm, and then it was like a full late snowstorm. That was it. Right? So climate change is happening. Look at the storms that are hitting Texas right now. You know, look at all the storms that are hitting the Northeast. We've had crazy storms. The past like 5 years, you know, I think my son was 3 years old before he had his first Halloween. There was a storm like excuse me, early snowstorm on the leaves stuff. Right, so therefore the trees weren't ready for it. The trees were falling all over the place. Power lines were down. It was crazy. You remember that storm? Probably like 4 or 5 years ago. And then you had Irene. Hurricane Irene, remember that one? It wasn't so much of a big deal here, but it's up a ton of rain going in up into Vermont. Like I know now still Vermont. Downtown. It was so much rain. That was a crazy storm. And then the year after that, it was Sandy. Right? So things are changing. That's just looking here. I mean, look at the storms that are hitting all in the south. Like the amount of rain being dropped in certain places is crazy. So the changes are happening. It's becoming more and more dramatic. We need to try to do something about it. It's linked to this. Okay. That's pretty much it. The key thing that we don't really mention here is how do organisms get the carbon in the carbon cycle? They get it by eating. The food chain is a part of this, so don't forget that. Nitrogen cycle. Out of all the cycles, it has the most complexity. Not really complex, but some things that are a little bit might be new to you. There's a lot of interactions here. Really, we kind of break it down to this. Okay, nitrogen cycle is pretty straightforward. So, what we have here is this. Everyone take a deep breath. You just breathe in a ton of nitrogen. Nitrogen actually has a fairly high concentration. Somebody Google real quick what percentage of our atmosphere is made up of nitrogen. 78% is nitrogen. Right? So therefore, when you breathe in, 78% of what you're breathing in is nitrogen. The problem with that is you can't do anything with it. You breathe it in, and you breathe it right back out. Nitrogen's diatomic. So nitrogen comes like oxygen, it's diatomic. I think there's 3 bonds there. And it's joined together. And we do not have the ability to break that bond down. So when you breathe in nitrogen, it could dissolve, it could get into your blood, it could float around your blood, but you can't do anything with nitrogen gas. So therefore you breathe it right back out. It's kind of bizarre. But here's the thing, we need nitrogen. So how do we get nitrogen? The real big player here is here. There's a process known as nitrogen fixation. And it's done by a bacteria known as nitrogen fixing bacteria. These nitrogen fixing bacteria, they're all over the place. They're in our soils, but they tend to concentrate near the roots of like legume type plants, which are beans, peanuts, things like that. They're really concentrated in the soils. It's why a lot of times people do crop rotation. They might grow corn, and then every once in a while they'll mix in some beans because it'll help to kind of foster the nitrogen fixing bacteria, help to foster nitrogen in the soil. So the key players here are these little bacteria known as nitrogen fixing bacteria. That's when you start, and they can take N2 gas and they convert it into ammonia. Once it's in ammonia, it can be absorbed by where does the whole matter come from in our food chain? It starts with right, it can be absorbed by plants. Right, so it can be absorbed by plants. There's another type of bacteria though. There's nitrifying bacteria, and they can take the NH3 and convert it into nitrates and nitrites. Nitrates and nitrites can be absorbed by bacteria. They can be absorbed by plants as well. Right? So there's just other nitrogen compounds. We need to complete this cycle. So we need to get this nitrogen, which is now in plants and animals because of the food chain. When animals and organisms die, it can kind of become a part of fossils and become part of sediment, things like that. But we need to get it back to the atmosphere. And that process involves what are you laughing at? What's funny? Now I'm interested. What's funny? What's going on? Don't make me throw a TV remote. Are you all right? Pay attention. Okay. So the nitrogen cycle is basically broken down like this. It's broken down into nitrogen fixation, nitrifying, and denitrification. Out of all these terms, the one you must know is the nitrogen fixation and nitrogen fixing bacteria. They are special bacteria that undergo this process. Not all bacteria do. Right? The other two components are key as well, but the nitrogen fixation bacteria, they're the ones that keep this thing rolling. Without them, we wouldn't have nitrogen in our food chain. Now, if you notice, on the top right-hand side, you can see atmospheric nitrogen fixation. Lightning, storms, enter your atmosphere can convert some nitrogen gas into like ammonia and other nitrogen type compounds. There is some things that can happen after, but bacteria are the real players in this cycle. Everybody okay? All right. So this is nitrogen fixation, kind of going through the key things. Right, denitrification, there's your little cheat sheet there. The last one is the phosphorus cycle. The phosphorus cycle is a little bit different. What's different about the phosphorus cycle compared to the water cycle, the carbon cycle, and the nitrogen cycle? It's smaller. We don't have 3 reservoirs. We only have 2, right? There's no atmospheric component here. We don't really get atmospheric phosphorus. But phosphorus is locked up in sediments, right? It's locked up in rocks. Erosion occurs, it gets absorbed into the food chain, remains in organisms die, and goes back to the ground. Right? There's no atmospheric component. So phosphorus cycle is pretty easy. Everybody good?